Here we go with some more chain rule practice. I believe we did 15 and 19 in class, so I'm going to breeze through them kind of quickly. Press pause if you want to try the problem, then press play to see the solution. So here I have a product, and I've got x times e to the negative x squared. I used product rule first, d last, but the d last requires chain rule. Here's the derivative of the exponent. And then I have last d first, the derivative of the first just being 1, so that doesn't require any numbers there. This can be simplified a little bit by getting rid of those parentheses that are around the first term and just rewriting it as a single expression. But then I noticed, hey, each term here has e to the x negative x squared, so I can factor that out and rewrite it this way. Just be aware that multiple choice questions on the AP will be rewritten, and whatever answer you got to begin with may not look like the choice in the multiple choice. 19 is similar. It's also e raised to a power, but there's no product rule of the basic functions. There is, however, a product rule up here in the exponent. Press pause. So here I have the derivative, and I have e to whatever it started with times the derivative of this exponent. And that exponent is x cosine x, and its derivative, we need to use product rule. So I have last d first plus first d last. Since my sign was negative, I just brought that sign out here. This doesn't need to be simplified further. So in 33, we have a product again. Each piece of the product, however, has another embedded function, so we'll need chain rule twice here. Press pause, give it a try. So like I said, I need product rule, and I have derivative of the first. So derivative of e to the x is just e to the x, and in this case it's e to the alpha x, times the derivative of alpha x. Alpha is a constant, so I just get the constant, drop the power down 1 in x. So here's derivative of the first times last. And then of course I have first times the derivative of the last. Again, sine's derivative is cosine, but the derivative of beta x is beta. This too does not need to be simplified further. So I have 3 more for you. We did 23 in class. If you need a quick refresher, we have a sum of 2 chain rule pieces. We're using power rule here. Drop the power down 1, but then I need the derivative of secant. Very similar, power rule here. Drop the power down 1, but then I need the derivative of tangent. I end up with 2 terms that are very similar. In fact, they're exactly the same. And I can combine my like terms to get, oh, stop that, to get 4 secant squared tangents. 29 we did not get to in class. Press pause and give 29 a try. You have 3 functions here. We have a squared, something squared, we have cotangent, and we have sine. So you're going to have to do chain rule 3 times. This is not product rule. We don't add the pieces together, but we will have to multiply derivatives of each piece. Press pause. Okay, so here I took the derivative and I said, okay, I need product rule. So that's why the 2 is here and cotangent is to the first power. But I keep what was in cotangent. That doesn't go away. Now I'm going to take the derivative of cotangent. I did the squared part. Now I need to do cotangent. Ah, and I have a mistake. Do you see it? I shouldn't have cosecant squared x. What was in cotangent before? Sine was in cotangent, so sine should be here as well. So let's fix this. Y prime should be 2 cotangents to the first power of sine x times the derivative of cotangent, which is negative cosecant squared, but my input here has to be the same as my input was for cotangent. So sine. Okay, now I take the derivative of what was in the cotangent squared, and that's cosine. There's my final answer. Number 43 used a table, and it said that h of x was equal to f of g of x. So the derivative of h of x would be f prime times g prime, f prime of g times g prime. They asked me specifically to find the derivative at x equals 1, so I needed some information about g of 1 and g prime of 1. G of 1 and g prime of 1 were in the table. The reason I looked for f prime of 2 is that, well, if g prime of 1 is 2, then what I really end up with is this. F prime of 2 times g prime of 1. Just making substitutions with the values I got. So I could substitute a 5 and a 6 and get 30 as my final answer. (52) asks about a twice differentiable function. Functions are differentiable if they are smooth and continuous. No kinks, no cusps, no holes, no asymptotes. And they're telling me that this function is differentiable, not just one time, but twice. So we can take its second derivative too. They want me to write an expression for the second derivative in terms of g, g prime, and g double prime. So I first need to figure out kind of in general what the derivative of f would be. Try that first. Press pause. So I realized I needed f prime and I need g prime. So let's see what we get here. F prime is firsty last, lasty first. So my first is just x times g prime of x squared. But then I need chain rule to take the derivative of x squared, 2x. That's where this term came from. Do you see how they're the same? Goody. Then I need for last d first. So here's my last term. The derivative of the first was just 1, but it's not written. So I needed g prime, that was here, and I put it into my f prime. Are we okay with that? Okay. Now I need to take the second derivative. So I need to take the derivative of my derivative. So the derivative of f prime, again, I have a product rule. First, last. I need product rule for this piece. But I'm also going to need chain rule for the g prime of x squared. So derivative of the first term, my 2x squared, became 4x times the last. That's just g prime of x squared right here. Then I need the first term, the 2x squared, times the derivative of g prime of x squared. Well, let's look at the derivative of g prime of x squared. I need the derivative of g prime, which is the second derivative of g, at x squared, times the derivative of what's inside, 2x. That's where this whole term came from. Okay? First, and then derivative of the last. So far, so good? Okay. This very last term here, we already know its derivative. We've used it before, so I can just plug that right in. And I'm done. That's what they asked for. Concavity. We've talked a little bit about concavity. If a function is concave down, its derivative, wait a minute, its derivative is decreasing. How do I tell if it's a derivative? Is it decreasing? Well, if a function is decreasing, that means its derivative is negative. So my function is concave down, which means f prime is decreasing. If f prime is decreasing, that implies that f double prime is negative. So these are the pieces I need to unfold before I actually do some calculus. Now that we know what we're looking for, what are we looking for? Where f double prime is less than 0. And in this case, it's actually a y, not an f. So we're looking for where y double prime is less than 0, because that's where f prime is decreasing. And if f prime is decreasing, the function is concave down. Go ahead and try. Press pause. So the first derivative is just negative 2x e to the negative x squared. We've done this derivative before on this very set of problems. My second derivative, I need to use product rule. Firsty last, lasty first. So here's first, and here's the derivative of the last. Here's the derivative of the first, and here's the last. Make sense? So now I need to find out where this second derivative is less than 0. If I can determine where it's equal to 0, I can then test on either side of that solution and find out where it is less than 0. Here you should solicit the help of your calculator. Graph these each as y's and find the intersection. Turns out your graph looks a little something like this. And these two intersections happen at negative 1 over root 2 and 1 over root 2. So then from the graph, I can see that my derivative function, which is graphed here, this is y double prime, my second derivative is less than 0 between these two values. So my answer to this would be between negative 1 over root 2 to 1 over root 2 in interval notation. Oh, look, we're done. Do the problems that I assigned and have a good night. Bye.